Section 7 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 7. Formulae, Equations, etc. Formulae and equations are a kind of shorthand for expressing briefly and in the language of the atomic theory the facts of chemical composition and reaction. The convenience of this method of expressing the facts justifies a short description of it here. On comparing the percentage compositions of a series of compounds, the proportions in which the elements combine appear to be regulated by no simple law. For example, in realgar, arsenic 71.4%, sulfur 28.6%, iron none, total 100%, orpiment, arsenic 60.9%, sulfur 39.1%, iron none, total 100%. Mispickle, arsenic 46%, sulfur 19.6%, iron 34.4%, total 100%. And pyrites, arsenic none, sulfur 53.3%, iron 46.7%, total 100%. But if in these examples the composition is calculated not on 100 parts, but on 107, 246, 163, and 120 parts respectively, evidence of a simple law becomes apparent. Realgar, arsenic 75.0, sulfur 32.0, iron none, total 107.0, orpiment, arsenic 150.0, sulfur 96.0, iron none, total 246.0. Mispickle, arsenic 75.0, sulfur 32.0, iron 56.0, total 163.0. Pyrites, arsenic none, sulfur 64.0, iron 56.0, total 120.0. It will be seen that the proportion of arsenic is 75, or twice 75, that of iron is 56, and that of sulfur 32, or some simple multiple of 32. The series of examples might be extended indefinitely, and it would still be found that the combining proportions held good. The number 75 is spoken of as the combining weight, or more frequently as the atomic weight, of arsenic. Similarly, 56 is the atomic weight of iron and 32 the atomic weight of sulfur. The importance of this law of chemical combination is altogether independent of the atomic theory, but this theory furnishes the simplest explanation of the facts. According to it, a chemical compound is made up of exactly similar groups of particles. The particles of each elementary substance are all alike, but differ from those of other elements in weight. Ultimate particles are called atoms, and the groups of atoms are called molecules. The atomic weight of any particular element is the weight of its atom compared with the weight of an atom of hydrogen. The atom of sulfur, for instance, is 32 times as heavy as the atom of hydrogen, and the atomic weight of sulfur is 32. The molecular weight is the sum of the atomic weights of the group. The molecule of pyrites contains 2 atoms of sulfur and 1 of iron. On referring to the table of atomic weights, it will be seen that the atomic weights are sulfur 32 and iron 56. The molecular weight, therefore, is 32 plus 32 plus 56, that is 120. The meaning of this is 120 parts by weight of iron pyrites contain 64 parts of sulfur and 56 parts of iron, and this is true whether the parts by weight be grains or tons. The symbol or formula of an atom is generally the initial letter or letters of the Latin or English name of the substance. The atom of hydrogen is written H, that of oxygen O, of sulfur S, of iron ferrum Fe, and so on. A list of these symbols is given in the table of atomic weights. The formula of a molecule is obtained by placing together the symbols of the contained atoms. Thus, Fe represents an atom of iron, S an atom of sulfur, while Fes represents the molecule of sulfide of iron as containing 1 atom of each element. When more than one atom of an element is present, this is shown by writing a figure under and after the symbol. Thus FeS2 represents a molecule with 1 atom of iron and 2 atoms of sulfur. Fe2S3 similarly shows one with 2 atoms of iron and 3 of sulfur. When a group of atoms is enclosed in brackets, a figure after and under the bracket multiplies all within it. For example, Pb open bracket NO3 close bracket times 2 is another way of writing PbN2O6. Sometimes it is convenient to represent the atoms of a molecule as divided into 2 or more groups. This may be done by writing the formulae of the groups and separating each simple formula by a full stop. Slaked lime, for instance, has the formula CaH2O2, or, as already explained, we may write it Ca open brackets HO close bracket times 2. Or, if for purposes of explanation we wished to look on it as lime, CaO, and water, H2O, we could write it CaO.H2O. A plus sign has a different meaning. CaO plus H2O indicates quantities of 2 substances, water and lime, which are separate from each other. The sign of equality is generally used to separate a statement of the reagents used from another statement of the products of the reaction. It may be translated into the word yields or becomes. The 2 statements form an equation. Ignoring the quantitative relation, the meaning of the equation CaO plus H2O becomes CaO.H2O is lime and water yield slaked lime. By referring to a table of atomic weights, we can elicit the quantitative relations thus: CaO plus H2O yields CaH2O2. CaO comprises Ca 40, O 16, total 56. H2O comprises H2, 2 from 1 times 2, O 16, total 18. CaH2O2 comprises Ca 40, H2, 2, O2, 32, 16 times 2, total 74. Or putting it in words, 56 parts of lime combine with 18 parts of water to form 74 parts of slaked lime. This equation enables one to answer such a question as this: how much lime must be used to produce 1 hundredweight of slaked lime? For if 74 pounds of slaked lime requires 56 pounds of lime, 112 pounds will require 56 times 112 divided by 74, or about 84 3/4 pounds. As another example, having a closer bearing on assaying, take the following question. In order to assay 5 grams of black tin, SnO2, by the cyanide process, how much potassic cyanide, KCN, will be required? The reaction is SnO2 plus 2 KCN yields Sn plus 2 KCNO. SnO2 comprises Sn, 118, O2, 32, total 150. KCN comprises K, 39, C, 12, N, 14, 65, times 2 equals 130. What is sought for here is the relation between the quantities of SnO2 and KCN. Note that a figure before a formula multiplies all that follows up to the next stop, or plus or equality sign. The question is now resolved to this: if 150 grams of oxide of tin require 130 grams of cyanide, how much will 5 grams require? 150 to 130 is equivalent to 5 to X. Therefore X equals 4.33 grams. A problem of frequent occurrence is to find the percentage composition of a substance when its formula has been given. For example, what percentage of iron is contained in a mineral having the formula 2Fe2O3.3H2O? Bringing this formula together, we have Fe4H6O9. Find the molecular weight. Fe4 equals 224 from 56 times 4. H6 equals 6 from 1 times 6. O9 equals 144 from 16 times 9. Overall total 374. Then we get 374 parts of the mineral contain 224 of iron. How much will 100 contain? 374 to 224 is equivalent to 100 to x. Therefore, x equals 59.89, and the answer to the question is 59.89%. Again, suppose the question is of this kind. How much crystallized copper sulfate, CuSO4.5H2O, will be required to make 2 litres of a solution, 1 cc of which shall contain 0.0010 of a gram of copper? A litre is 1000 cc's, so therefore 2 litres of the solution must contain 0.001 of a gram times 2000, or 2 grams. How much crystallized copper sulfate will contain this amount of metal? Cu equals 63.3, S equals 32.0, O4 equals 64.0, from 16 times 4. 5H2O equals 90.0, from 18 times 5. Overall total 249.3. If 63.3 grams of copper are contained in 249.3 grams of sulfate, in how much is 2 grams contained? 63.3 to 249.3 is equivalent to 2 grams to x. Therefore, x equals 7.8769 grams. The answer is 7.8769 grams must be taken. As a sample of another class of problem similar in nature to the last, but a little more complicated, take the following. What weight of permanganate of potash must be taken to make 2 litres of a solution, 100 cc's of which shall be equivalent to 1 gram of iron? In the first place, the 2 litres must be equivalent to 20 grams of iron, for there are 20 times 100 cc's in 2 litres. In the titration of iron by permanganate solution, there are 2 reactions. First, in dissolving the iron, Fe plus H2SO4 yields FeSO4 plus H2, where the atomic weight of Fe is 56. And second, in the actual titration, 10 FeSO4 plus 2 KMnO4 plus 9 H2SO4 yields 2 MnSO4 plus 5 Fe2 open brackets SO4 close brackets times 3 plus 2 KHSO4 plus 8 H2O, where KMnO4 consists of potassium 39, manganese 55, O4 64, total 158, and total for 2 molecules 316. As before, attention is confined to the 2 substances under consideration, that is, Fe and KMnO4. In the second equation we find 316 parts of the permanganate are required for 10 molecules of FeSO4, and in the first equation 56 parts of iron are equivalent to 1 molecule of FeSO4. Therefore 560 of iron are equivalent to 316 of permanganate. And the question is, how much of the permanganate will be equivalent to 20 grams of iron? 560 to 316 is equivalent to 20 grams to x. Therefore, x equals 11.286 grams. The answer is 11.286 grams. Very similar to this last problem is the question suggested under the head Indirect Titration. Reader's note. In Chapter 4, Volumetric Assays. End note. If 100 cc's of the standard permanganate solution are equivalent to 1 gram of iron, how much peroxide of manganese will they be equivalent to? The equation for dissolving the iron is already given. The second equation is 2 FeSO4 plus MnO2 plus 2 H2SO4 yields Fe2 open brackets SO4 close brackets 2 times plus MnSO4 plus 2 H2O. MnO2 consisting of Mn 55, O2 32, molecular weight 87. It will be seen that 87 grams of peroxide of manganese are equivalent to 112 grams of iron. How much then is equivalent to 1 gram of iron? 112 to 87 is equivalent to 1 gram to x. Therefore x equals 0.7767 of a gram. It is sometimes convenient to calculate the formula of a substance from its analysis. The method of calculating is shown by the following example. Required, the formula of a mineral which gave the following figures on analysis. Cupric oxide, CuO, 10.58, ferrous oxide, FeO, 15.69, zinc oxide, ZnO, 0.35, sulfuric oxide, SO2, 28.82, water, H2O, 44.71, total 100.15. First, find the molecular weights of CuO, FeO, etc., and divide the corresponding percentages by these figures. Thus, CuO equals 63.3 plus 16 equals 79.3, and 10.58 divided by 79.3 gives 0.1334. Similarly, FeO equals 56 plus 16 equals 72, and 15.69 divided by 72 gives 0.2179. Treated in the same way, the oxide of zinc, sulfuric oxide, and water give as results 0.0043, 0.3602, and 2.484. Classify the results as follows. Bases: CuO 0.1334, FeO 0.2179, ZnO 0.0043, total RO 0.3556. Acids: SO3 0.3602, total RO3 0.3602. Water H2O 2.484 equals R2O 2.484. The figures 0.3556, 0.3602 and 2.484 should be then divided by the lowest of them, that is 0.3556, or where, as in this case, two of the figures are very near each other, the mean of these may be taken, that is 0.3579. Whichever is taken, the figures got will be approximately 1, 1 and 7. The formula is then RO.SO3.7H2O, in which R is nearly 2/5 copper, 3/5 iron, and a little zinc. This formula requires the following percentage composition, which for the sake of comparison is placed side by side with the actual results. Cupric oxide, calculated 11.29, found 10.58. Ferrous oxide, 15.37, found 15.69. Zinc oxide, calculated nil, found 0.35. Sulfuric oxide, calculated 28.47, found 28.82. Water 44.84, found 44.71. Calculated total 99.97, found total 100.15. Trimming the results of an analysis to make them fit in more closely with the calculations from the formula would be foolish as well as dishonest. There can be no doubt that the actual analytical results represent the composition of the specimen much more closely than the formula does, although perhaps other specimens of the same mineral would yield results which would group themselves better around the calculated results than around those of the first specimen analysed. It must be remembered that substances are rarely found pure, either in nature or in the arts, so that in most cases the formula only gives an approximation to the truth. In the case of hydrated salts, there is generally a difficulty in getting the salt with exactly the right proportion of water. Practical exercises. The following calculations may be made. 1. Calculate standards in the following cases. A. Silver taken 1.003 gram. Standard salt used 100.15 cc. B. Iron taken 0.7 gram. Bichromate used 69.6 cc. 2. Calculate percentages. A. Ore taken 1 gram. Solution used 65.2 cc. Standard 0.987 gram. B. Ore taken 1 gram. Barium sulfate got 1.432 gram. Barium sulfate contains 13.73% of sulfur, and the percentage of sulfur in the ore is wanted. C. Barium sulfate is BaSO4. Calculate the percentage of sulphur it contains for use in the preceding question. 3. A method of estimating the quantity of peroxide in a manganese ore is based on the following reactions. 1. MnO2 plus 4HCl yields MnCl2 plus Cl2 plus 2H2O. 2. Cl plus Ki yields KCl plus I. To how much MnO2 is 1 gram of iodine, I, equivalent? 4. A mineral has the following composition: carbonic acid, CO2, 19.09, copper oxide, CuO, 71.46, water, H2O, 9.02. What is its formula? 5. How much copper is contained in 1.5 grams of crystallized copper sulfate, CuSO4.5H2O? How much of these crystals must be taken to give 0.4 of a gram of copper? 6. How much ferrous sulfate crystals, FeSO4.7H2O, must be taken to yield 2 litres of a solution, 100 cc of which shall contain 0.56 of a gram of iron? 7. Galena is PbS and hematite Fe2O3. What percentages of metal do these minerals contain? End of section 7.